Hello and welcome to my videos on prime numbers. This is my first analysis video on prime numbers. So we know what a prime number is, but let's get a little bit more analytical and technical. The purpose of these videos is to look deeper and find out the special properties and characteristics of primes. Let me ask you a question. How many primes are there less than or equal to 100? 1,000, n, any n, up to infinity? Good question. Ponder over that if you will, but it's not entirely obvious, is it? We can use various techniques to find primes, or as I like to put it, reveal primes. The reason I say reveal will become clear soon. So let's start with the case less than or equal to 100. So in essence, we want to count the number of primes up to 100. Now remember, we are not including 1 as a prime. So the first prime is 2. 2 is very special because it's the only even prime and is essentially the bedrock of all even numbers. Every even number has 2 as a prime factor. To illustrate this, consider the sequence of evens 2, 4, 6, 8, 10, 12, 14. If we divide by 2, we obtain 1, 2, 3, 4, 5, 6, 7, and so on, which is every integer or the natural numbers. We will exclude 0 as it's trivial. A little point on 0 though. Technically every non-zero integer is a factor of 0, but that's not very exciting, as this means the other paired factor is always 0, i.e. n times 0 equals 0, 0 over n equals 0. However, this is all we can say. We cannot say 0 over 0 equals n for any given n. Here n is indeterminate. It can in theory be any number. So a word of caution, if you see 0 over 0, it does not equal 1. 1 over 1 equals 1, 2 over 2 equals 1, 3 over 3 equals 1, n over n equals 1, as long as n is not 0. So 0 over 0 is indeterminate. Okay, so pardon me for the digression. Let's now tackle the quest to find all primes up to 100. I'm going to use sieve techniques for this. We basically cross out all the composite numbers up to 100 and we are left with the primes. So earlier I said reveal, so this is what I meant when I said reveal. I meant that by crossing out all the composites, the primes will appear because that's all we're going to have left. So they, in a way, they're revealing themselves to us. So let's draw a nice 10 by 10 grid. 10 by 10 is 100, obviously. So this is my grid. And what we're going to do now, I'm going to pause the video and I'll be back in a few seconds, because what we're going to do, we're going to cross this grid out together in real time. So this should be a fun exercise. And we're going to be left with the primes. Okay, so let's get started. Now we're going to exclude 1, as I said earlier. So I'm going to highlight that in a blue color because 1 is very special. So we're not classifying 1 as prime, but we're not classifying it as composite either. So I'm going to highlight that in blue. Now we already proved that 2 was prime. We know 2 is prime. There are no integers between 1 and 2 which divide 2. We've only got 1 times 2 equals 2, so 2 is definitely prime. So I'm going to highlight that in green. Give it a green background, sorry. Yeah, so 2 is prime. Now, we're now going to cross out all multiples of 2, because anything which is divisible by 2, apart from 2 itself, is composite, i.e. not prime. So that's basically every even number apart from 2. So we can cross all of them out. So for example, if you look at the columns, look at the column with all the numbers with 2 at the top, every number underneath ends in 2. 12, 22, 32 down to 92. So these are all even. And then if you look at the column with 4 at the top, 4, 14, 24, 34, etc. down to 94, then 6 at the top, 8 at the top, 10 at the top. So all these columns can be crossed out. The full column can be crossed out, apart from the one with 2 at the top. Only 2 qualifies. Every other even number on that grid is composite, so we can cross all them out. So we can either delete them from the grid, or we can highlight them in red. I'm going to highlight them in red. So this could take a little time. So what I'm going to do, I'm going to pause the video and I'll be back with you in a second once I've highlighted all these even numbers. Okay, so I've highlighted all the even numbers in red, apart from 2, which is green, because 2 is prime. So we want to find the prime numbers. So the prime numbers will be highlighted in green. Okay, so what else can we cross out? Well, basically, if we start from 1 and work our way up towards infinity, and we take every multiple of each number. So we've done 2. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on. You can see that from the red numbers. So now we need to do 3. Now, because 3 is the first number that we've not checked, it automatically becomes prime. Because we're starting from 1, remember? So as long as you start from the beginning, and you've checked every number before that number, and you've done all your crossing out, then the next number has to be prime. I'm not going to prove that in this video, but just trust me on that. So 3 is prime, so I'm going to highlight that in green. So now we're going to use that as our multiple. So that means every multiple of 3, apart from 3, is composite. So we can cross all of them out. So that includes numbers like, well, if you include 3, we'll include 3 for a minute, just to make life simple. So if you take the sequence 3, 6, 9, 12, 15, 18, 21, and so on. So these are all divisible by 3. So these are all composite apart from 3 itself. So we can cross out every single number in that sequence apart from 3. So the first one that we can cross out is 6. Oh, but we've actually already crossed 6 out. 6 was crossed out because of 2, because 6 is also a multiple of 2, and 6 is even as well. So that was crossed out earlier. So that's good, so we don't need to cross that out. But 3 would have crossed it out as well. So the next one is 9. 9 hasn't been crossed out, so we can cross 9 out. So let's cross 9 out. What comes after 9? 12. Oh, that's already done. What's next? 15. That hasn't been done, so we can cross that out. So I think you can see what's happening here. Every second number is even, so they've already been crossed out. So for example, 6 and then 9 is odd, and then 12 even, 15 odd, 18 even, 21 odd, 24 even, 27 odd, and so on. So we can actually just ignore all the evens because they've already been crossed out. So we only really need to focus on the odd numbers. And back to what I was saying earlier in a previous video, every prime number is odd apart from 2. So when we're doing our crossing out, we don't even need to worry about even numbers anymore. Plus, they've already all been crossed out. So when we're taking a sequence like 3, 6, 9, 12. So that's an arithmetic progression that has a common difference of 3. So what we want to do is we want to take the first number, which is 3, which is odd. We want to double the common difference to 6. So we turn the sequence into a arithmetic progression with a common difference of 6 instead of 3. The reason we do that is so that we skip the evens. So now we're going to have 3, 9, 15, 21, etc. It's just a little trick for convenience. Okay, so we've struck 9 out, so let's add 6 to that. Strike out 15, add 6 to that, we get 21, strike that out. Add 6, we get 27, strike that out. Add 6, we get 33, strike that out. Keep going, the next one's 39. You can count them with me. I'm beginning to enjoy this. This takes me back. We used to do similar things in primary school. So yeah, let's keep crossing these out. The next one is 57. So we're just adding 6 on each time. 69. And we're nearly finished. We're not far away from 100 now. Now we're down to 81. 87. 93. And 99. So there we go. We've now crossed out all multiples of 3 less than or equal to 100, apart from 3 itself. Okay, so apply the same principle I told you earlier. Move on to the next free number in the grid that we haven't looked at yet, we haven't touched, so that's 5. Now we've used 2 and 3 already. 4's crossed out, so the next free one is 5, so that is automatically prime, if you remember what I said earlier. Just trust me on this, guys, okay? So that's prime, so now we want to strike out every multiple of 5 apart from 5. So 5, 10, 15, 20, 25, 30, 35, 40. Now some of these we will have already crossed out because of 2 and 3. But let's just go through it anyway. So 5's prime, 10's already out because that's even. 15's already out because that was crossed out by 3. 20's already out because that's even. 25 is not crossed out yet, so we can cross that out. 30's already out because that's even. 35 is not crossed out yet. 40's crossed out because that's even. So again, if you remember what we did when we were doing it for 3, we took the arithmetic progression, we took the common difference, which was 3 in that case, we doubled it to 6. So now we have 5 as our common difference, so we double that to 10. So if you start from 5 and you double your common difference to 10, you're going to end up with a sequence 5, 15, 25, 35, 45, 55, 65. Oh, that's just this column, isn't it? That's just the column with 5 at the top. So we can strike that whole column out, apart from 5, of course. So let's just strike those out. So that means we can strike all these out, the ones. And what you'll notice, there's something I want to bring to your attention here about these. So I've struck out all the numbers in that column. What you'll notice about that column, guys, is they all end in 5. Every number ends in 5. The last digit is 5. And in general, if a number has a last digit of 5, it's composite. Apart from 5 itself. 5 is the only prime number ending in 5. So if you extend that grid to infinity, the next one would be 105, 115, 125. So they're all crossed out. They're all composite. So that's good. So we've done that. So the next free one is 7. So that's prime. And then again, we want to do multiples of 7, but we'll skip the evens. So double the common difference, you get 14. So 7 plus 14 is 21. Oh, we've already done that because that was crossed out by 3. Next one is 35. Oh, we've done that. That's crossed out by 5. The next one is 49. That's not crossed out yet. Let's cross that out. The next one is 63. That's already crossed out. The next one is 77. That's not crossed out yet. Let's cross that out. The next one is 91. That's not crossed. Let's cross that. And that's it. So there are no more odd numbers, which are a multiple of 7, that we haven't crossed out yet. Oh, the grid's becoming very red, isn't it? There's not a lot of primes in there, guys, is there? Okay, so the next one is 11. The next free number is 11, so that's going to be prime. And we want to cross out every odd number, which is a multiple of 11. Ignore the evens, so ignore 22, 30, and 44, etc. So the next one will be 11 plus 22, so it's double the number. That's your common difference, so it's 22. Keep adding 22, you get 11, 33, 55, 77, 99. Now I'm going to show you something really cool here. Now watch this. If you look where 11 is positioned on this grid, right? And if you want to find the next number, which is a multiple of 11, you just basically go down the diagonal in a southeasterly direction. So look at this. I'm gonna just highlight a couple of the numbers. So there's 11, there's 22, there's 33, 44, 55, 66, all the way down to 99. They're in a nice diagonal there. You can see that, yeah? Now we've actually crossed them all out because they all got crossed out by previous multiples of previous prime numbers. So that's good. So we can skip 11 now. So we've done 11 basically from the previous numbers. But I just wanted to show you that cool diagonal there, guys. Now, if we were doing 11 on its own, in its own merits, and we hadn't checked any other numbers, then we would apply that principle I told you, 11 plus 22. So you would look at 33 first, cross it out, then you'd cross out 55, 77, and 99. But a quick way would be just to go down that diagonal. Okay, so let's go for 13 now. So 13 is prime because that's the next free number. Make it green. Now we double the number to get the common difference is 26. So the next number will be 39. Add 26 to 39, you get 65. Add 26 to 65, what does that give you? That gives you 91. So we're done. We've actually done all of 13. Next number is 17. So make it green, that's prime. Now 17, double that, you get 34. Add that onto 17, you get 51. 51's already done. Add 34 to that, you get 85. That's already done. So that's 17 done. Now I'm going to change the technique slightly now, just to save a little bit of time, because we're running out of numbers and the primes are starting to reveal themselves. So 19 is going to be prime. So to find the next odd prime, which is a multiple of 19, the next composite, which is a multiple of 19, odd number, then we're going to multiply it by, well, 19 times 1 is the first one, so we ignore that, that's prime. The next one will be 19 times 3, which is 57. So that's already done because 3, remember we've already crossed out multiples of 3. The next one will be 19 times 5, 95. But that's already done because we've already crossed out multiples of 5. So we're done. Then 23. So now we're just sort of running into primes almost all the time now. Again, 23 times 1, that's prime. 23 times 3, we've already done it because it's a multiple of 3. 23 times 5, well, that's greater than 100, so we don't need to worry about that. So we're done. The next one is 29. 29 times 1, 29. 29 times 3, 87, but that's already done because it's a multiple of 3. 29 times 5 is over 100, so we ignore that. Okay, now we're on to 31. Prime. Times 3 is 93. composite, multiple of 3. Next one, 37 prime times 3, 111. Well, that's greater than 100, isn't it? So we can ignore that now. So we don't even need to check any of the other ones because we don't multiples of 37, sorry, because they're all going to be over 100, right? So based on that, that means we're basically done, because the next one is definitely going to be prime because we've not checked it or crossed it out yet, 41, and the next odd multiple of 41 is going to be 41 times 3, and that's greater than 100. So it's not going to be in this grid, so we won't be able to cross any more out. And that will also apply to 43 and so on. So we're basically done, guys. So once we got up to number 37, our work is done. And then that means every number after that is prime. The ones that we haven't crossed out yet. All these white boxes, these are all prime. So I'm just going to make them green because it looks nicer. So let's just make all these green. Now we could go and check them all, but what's the point? We're done. So it just shows you the power of sieve theory. Sieve techniques mean that we don't need to check every single number. We only checked up to roughly a third of the numbers. Up to, say, well, when we got to 33, if you multiply 33 by 3, you get 99, which is almost 100, and that was already crossed out anyway. So yeah, we could have actually stopped there. And then 37 is automatically prime, and so is all the rest that we haven't crossed out. So yeah, we could have actually stopped at 33, which is roughly 1/3 of the numbers. So it just shows you the power of sieve theory. So let me just let me just make all these primes green. So there we go, we're done. So now what we're going to do, we're going to count these. So how many is there? Let's count them. So in the first row, I'm going to count them row by row. In the first row, we've got 1, 2, 3, 4. We've got 2, 3, 5, and 7. And they're the most famous primes. You'll see them. If you read anything about primes, they'll always be listed as examples. You know, because you obviously want to write down simple primes if you're trying to explain what primes are. So they're the most famous primes, and they're also the most, they're the only primes, single-digit primes. Every prime after 7 has double digit or more. So 11, for example, that's got 2 digits. So they're all 2 digits after that. After 97, they're all triple digits. So yeah, so we've got 4 in the first row. How many in the second row? We've got 11, 13, 17, 19, 4 there. So that's 8. 23 and 29, that's 2, that's 10. 31 and 37, that's 12. 41, 43, 47, 15. 53 and 59, 17. 61 and 67, 19. 71, 73, 79, 22. 83 and 89, that's 2, so that's 25. And then 97 is 1, that's 26. So I count 26. Remember, we're not including 1. So let's just double check that. I've counted 26. You can count it as well. I'm going to just count it one more time to make doubly sure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, sorry, 25. I must have double counted. So I'll do it one more time. I'll do it by the columns this time. So I've got 5 in the first column, 1 in the second column, 6, 7 in the third column, 1 in the fifth column, 6 in the 7th column, 5 in the 9th column. So add those together, what do you get? So that will be 5 plus 1 is 6, plus 7 is 13, plus 1 is 14, plus 6 is 20, plus 5 is 25. Yeah, so there's 25 primes less than or equal to 100. So that's a quarter, guys. That's exactly 25%, exactly 1/4. So if you put 100 numbers in a box or a bag and shake them, and I ask you to pick one out, the probability that that number is prime is 1 in 4. So it's a quarter. So that's very interesting. So now you can impress all your friends if they ask you how many primes are there less than or equal to 100. The answer is 25. Okay, so what can we do with this? Well, we've only really used a small sample size of 100, obviously. If I asked you to do it up to 1,000, it's obviously going to take you a lot longer. You can apply this sieve technique we just applied, and it'll obviously take you a lot more time. Nowadays, we use computers to do these kind of things, and we now know the number of primes up to gigantic numbers. I mean, I'm not even going to write the number down. Numbers that you wouldn't even think of, just huge numbers. So we know the number of primes. And the techniques used involve sieve techniques and a few other techniques that I won't cover in this video, and obviously with the assistance of very powerful computers to do all the computations and crossing out and different things. So, but the purpose of this, why I wanted to discuss all of this, is that there's a thing called the prime counting function. So what that does, it approximates, it counts all the primes up to a given number, but then it also approximates how many there is for a given number. So if you give me a number like 1,000 or 1,000,000, this function can approximate pretty accurately how many primes there is. We're not going to cover it in this video, but one thing I will say, it's not a quarter. There's no fancy simple formula here. It's definitely not a quarter. It's only a quarter for up to 100, but as you get larger and larger towards infinity, that ratio actually comes down. It drops and drops and drops. I mean, let's just demonstrate that. Think about it. I mean, look at the first 10 numbers, for example. So for the first 10, we had 2, 3, 5, and 7, which is 4 out of 10. That's 40%. Right? And then for the first 20, it's 8, so that's still 40%. But then for the first 30, it's 10, which is 10 over 30, which is 1/3. So that's a wee bit less, isn't it? It's dropping already. And then for 40, it's 12. So that's 12 over 40. So that's 3/10, I think. Yeah, was that 3/10? So yeah, I mean, it's dropping all the time. And by the time you get to 100, it's down to 25%. So it starts off high and then it drops off. We will analyze this in more detail in another video. But this was just to give you an idea of ways to count the primes and some little tricks and to notice some patterns in the primes. So I'm going to pause the video now and we're going to discuss another few details about primes. So I'll be back in a moment. So as we can see, sieve theory is very powerful and we are done at 33. We didn't need to check all 100 numbers. So the number of primes up to 100 is 25. The probability of a prime between 1 and 100 is 1/4 or 25%. So we learned some tricks along the way which greatly speeds up our work. So thanks for watching my prime number video, my first analysis of primes video. Subscribe to my channel and I'll see you again soon. Thank you.